Hello everyone, welcome to the Edexcel Physics past paper solution. This is Edexcel IAL Physics Unit 2 Summer 2018 Part 3. Let's start. Question number 17. The photograph shows a new design of car that can travel with minimal operation from the driver compared to the conventional cars. The new car contains system to detect other vehicle. One system uses a pulse echo technique with laser light, and another system uses the Doppler effect with microwave. One of these new cars travel behind a truck. Both vehicles are traveling at the same speed. Pulses of laser light are transmitted from the new car, and the time taken for each reflected pulse to return is measured. The time between the pulse being transmitted and returning is measured as 2.6 times the power minus 7 seconds. Calculate the distance between the new car and the truck. Clearly, it is a typical question of pulse and echo. And in pulse and echo, we have some obstacle, something like this, and you send an pulse and echo from some pulse like this. This is a pulse, and then it is reflected and received at the same point. So this is transducer, sender, and the receiver are here. So clearly you can see that the distance traveled by the light or signal is S is 2 into D, twice of the distance. So total distance is double. So you can use equation S is equal to UT to figure out the distance. But here the most common mistake generally students do is as they use S instead of S. Remember, it is pulse and then echo going and returning. So in place of S you should use either 2S or 2D. So 2D is equal to U into T, and then D is equal to UT upon 2. So 3 into 10 raised to the power 8, it's a laser light, and times T is 2.6 into 10 raised to the power minus 7 divided by 2, and D is 39 meter. Part B, the speed of the truck decreases. Explain how the new car uses the Doppler effect with microwave to detect that the speed of the truck has decreased. So in this case, what happened? If this is the car going behind, and this car is emitting microwave with some wavelength, and this wave hit the car, and then it is going in that way and then reflecting back and receive. So if the car and the truck maintain their constant distance, that means the wavelength between sent wave and the received wave will be same. But what happened when the speed is decreased and the truck starts coming closer and closer? That means wavelength of the received microwave will be decreased. That means the wavelength that the car is sending and the wavelength the car is receiving will be different. So there will be a change in the wavelength, and this change in wavelength can be used to figure out the new speed of the truck. Part 2. The new car automatically applies the brakes when it detects that the speed of the truck has decreased. Explain why the introduction of the new car may reduce the traffic accidents. It is okay. Clearly, because it is, you can say, a kind of a computer controlled car, some kind of, because it is automatically applies a brake. That means there will be almost no, or you can say negligible reaction time. So there will be a very less chance to for accident, as well as because everything is calculated automatically, so car can maintain a safe distance from the truck. So that's how we can reduce road traffic, by using these automatic control car. Question number 18. A 9-volt battery of negligible internal resistance is connected as shown. 9-volt battery, okay, two resistors. Calculate the potential difference across 120 ohm resistor. You can see that two resistors are connected in series with some power supply. This is a simple potential divider circuit, and in this case, if you need to find the voltage across any one of the resistors, so formula is V1 is equal to R1 upon R1 plus R2 into voltage of the source. So we need to find the potential difference across 120. So I can say that, okay, fine, this is my R1, this is my R2, and this is Vs. Voltage across 120 is V1. Across R2, the voltage is V2. If we need to find V1, so V1 would be equal to 120 divided by R1 plus R2, total resistance, which is 120 plus 110, so 230, into Vs, which is 9. So V1 is equal to 4.7 volt. This is the voltage across 120 ohm resistor. Part 2. A student added to the circuit as shown below in order to determine the resistance R of a resistor. A variable resistor is there. As the student adjusted the variable resistor, the reading on the voltmeter changed. When the variable resistor had a resistance of 295 ohm, the reading on the voltmeter was 0. Okay, this is key point. This happened because the potential difference across the variable resistor was equal to the potential difference across 120 ohm resistor. So potential difference across these two will be same. So R and 110. Show that the value of R is about 300 ohm. So remember, whenever you have these types of arrangement, if you see this closed loop where two resistors are parallel and then the other two parallel, in between we have a voltmeter, and if we have a voltmeter reading 0, that means ratio between the resistances R1 R2 R1 upon R2 must be same as R3 upon R4. So I'm considering this is R3 and this is R4. So, and this is only if we have a voltmeter showing 0 reading. So we can use this approach. We can figure out after substituting the values, that means 295 divided by 120. This is R1 and R2. R1 is 295 resistance of variable resistor, is as same as R divided by 110, and then you can rearrange, you can figure out R, and R will be approximately 270.4 ohm, or you round it off, you can say 270 ohm. A different form of the circuit is shown below. The 120 ohm and 110 ohm resistors were replaced with a wire XY of length 1 meter. R is 300 and variable resistor was altered to different value. The student moved the probe attached to the voltmeter along the wire. So this is the probe along the wire until at W. The reading on the voltmeter was 0 again. This occurred when the length XW is 33 centimeter. Calculate the resistance of the variable resistor, assuming that XY has a uniform cross-sectional area. Again, same question. Instead of resistances, they gave us the length, and you know that resistance is proportional to the length, so we can use length as the resistances. So you can say that if I say at that moment the variable resistance has the resistance, let's suppose X, this is unknown resistance, so you can say that X upon 33, the length of XW is equal to 300 divided by 67, and this is the length of YW or WY. This is 67 and this is 33, and you can figure out from here X is equal to 147.76, or you can round it off 148 ohm. This is the resistance of variable resistors. The student discovered that the wire was thinner between XW than it was between Y and W. Okay, W and Y. Explain why the result in an error in the calculated value of the resistances of the variable resistors. Clearly, you know that the resistance of any wire is inversely proportional to the area. That means thinner the wire, higher the resistance. That means the resistance of XW will be higher than WY. So you can say that thinner the wire has high resistance, so the value of the variable resistor must be higher, because the resistance of XW will be higher, thinner at XW. XW region has high resistance. This has high resistance, and if you see your arrangement, X upon 33 equal 300 over 67, and if you send on the other side, and clearly this number is showing resistance of thinner region, so X must be higher. That's how we can write. Describe how the student could check that the diameter of the wire is uniform. A typical question about the diameter of a wire, and we say that we are going to use micrometer screw gauge. A student should use micrometer screw gauge and measure the diameter at different places, or you can say orientation, and take the mean value in order to get accurate reading. Question number 19. A gold leaf electroscope is a device that can be used to detect charge. The deflection of the gold leaf depends on the amount of charge on the zinc plate and the conducting rod. Okay, so this is the gold leaf, conducting rod, zinc and insulation. In the demonstration of the photoelectric effect, a teacher charged the zinc plate with a negative charge and the gold leaf was deflected. When ultraviolet radiation of frequency 2 into 10 to the power of 15 Hz was shown onto the zinc plate, the deflection of the gold leaf reduced. Explain why the deflection of the gold leaf reduced. Your answer should include a calculation. So what happened when ultraviolet light hit the zinc plate? Some electron comes out from the plate that causes amount of charge in the insulating rod or in the gold leaf to reduce. That's why the deflection reduced. So you need to calculate whether the light has sufficient energy to emit electron or not. So we are going to calculate E is equal to HF. This is the energy of incident ultraviolet photon. H is Planck's constant. H is 6.63 into 10 raised to the power minus 34 into frequency. Frequency is 2 into 10 raised to the power 15 Hertz. So you can multiply, you can figure out E is equal to 1.3 into 10 raised to the power minus 18 joule. This is the energy of incident photon. And if you see at the bottom of the question, work function of the zinc is 6.9 into 10 raised to the power minus 19 joule. This is the work function. That means minimum energy required to emit an electron from the metal. So clearly your incident photon energy is greater than the work function. That's why electron comes out from the zinc plate and reduces charge inside the gold leaf and the conducting rod. That's why deflection reduces. Explain what would be observed with the gold leaf electroscope if ultraviolet radiation of the same frequency but with a lower intensity was used. So same frequency. If frequency is same, that means energy of incident photon will be same. So no change of the energy. That means electron is still going to emit from the zinc plate, but due to lower intensity, number of incident photons are decreased. So number of photons decreases, due to which less electrons are emitted from the plate. Less electrons are emitted. That means there will be a deflection in the gold leaf, but with a less rate. It will be reducing the distance between the plate and the conducting rod with the quite slowly, not quickly. It's less quickly. Part B, in the early 20th century, the wave model was generally accepted as an explanation of the nature of light. Explain why the wave model cannot explain the photoelectric effect. So we cannot explain photoelectric effect with the help of the wave model? It is because according to wave model, energy of the wave, energy of a wave, or you can say light, depends on intensity of the light. So we can expect that if we increase the intensity, if intensity is increased, then we can expect that energy of the emitted electron should be increased, but it is not observed. Change of intensity only causes the change in amount of current, but not the energy. This is the first drawback. And the second drawback, according to wave model, there must be some delay in emission of electron, because wave takes time when it when it absorbs into the metal, it takes time. So according to wave model, there must be some delay in emission of electron, but the observations are that electrons are emitted instantaneously rather than slowly. So that's how we have some flaw in wave model in explaining a photoelectric effect, and you can reframe your answer like that. Thank you very much for this video. Have a nice time. See you in the next one.